Okay, so in this question in this video we're going to look at question 4, again in two parts, A and B. Part A is asking you to use the laws of set algebra, of course, which you'll have in the handout to the exam, to use the laws of set algebra to show that A union B is equal to this triple union expression here on the right. This exponent C, of course, is the complement operator. Indicate clearly which of the laws you are using at each stage. Okay, so let's see. One way to prove this. I'm not claiming this is the only way to prove this, but I think this one seems the most straightforward. So I've got the way I've proved it here is I've started with the right-hand side of the equation, the triple union. And then I proceed applying one law at each stage, so until I arrive at the simplified expression A union B at the end. Okay, so first of all, we focus on the union of these two sets at the end. Okay, because what we notice here is each of these two sets we're taking the union of, they both are an intersection with B. So if we examine the distributive law of how intersection distributes over union, we see that the union of these two sets at the end here is exactly the intersection of B with the union of the two sets, of the other two sets of A complement union A. So this step here is justified by the distributive law. So the first set here, A intersection B complement, I've just left here unchanged, and we have the union of that with the set that follows it. Okay, so now we're looking at this as the intersection of B with the union of A complement and A. Okay, the noticeable thing there is you've got the union of A complement and A. So A complement is by definition everything in the universal set which is not in the set A. So when you take the union of that with A, you then have everything that's in the universal set. So that's called a complement law. So we can replace A complement union A with the universal set. But then we've got the intersection of a set with the universal set. But the universal set contains all that there is in this discussion. So when you take the universal set intersect any other set B, you're just going to get exactly what that other set is, namely B in this instance. So that's what's called the identity law. So we're doing some good simplification work here. And now we're faced with the union of B with this intersection here, A intersection B complement. So we can make use of a distributive law. Again, the other distributive law, which deals with taking the sorry, I lost my train of thought there, which deals with taking, how a union distributes over an intersection. So this is going to be A union B intersection with B complement union B. So that's again justified by the distributive law. Then again, you've got the complement law here, B complement union B. This reduces to the universal set. And then you've got another identity law application here because you got the intersection of a set with the universal set. So that's just equal to the other set, A union B. So going step by step there, we can proceed from the right-hand side of the given equation in the question back to the left-hand side. And now looking at part B, it asks us to write down the inverse and converse of this implication statement here, which says if an integer is divisible by 2, then the integer is an even number. And then using truth tables, verify that an inverse and converse of an implication are logically equivalent. Okay, so you want to think of this statement as, okay, well, I'll use P and Q. The statement here is of the form P implies Q. If P, then Q. Where P is the statement that an integer is divisible by 2, and Q. Hi there. Okay, sorry, I just got disturbed there. So this statement, think of it as P implies Q. So P is the statement that the integer is divisible by 2, and Q is the statement the integer is an even number. So the inverse will be not P implies not Q. So if an integer is not divisible by 2, then the integer is not an even number. The converse is the implication between P and Q, but in the reverse direction. So the converse would be if an integer is an even number, then the integer is divisible by 2. Okay, so the truth table part is we're asked to show that the inverse of an implication is logically equivalent to the converse. So to do this, well, the two statements we're looking at, the inverse and the converse of an implication P implies Q, so they involve P, Q, and their negations. So we begin our truth table with two columns showing the possible truth values for the pair P and Q. So there are 4 possibilities: true, 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 false, false, true, and false, false for P and Q in that order. Okay, then we need the negations. So not P is going to be false, false, true, true. So just negating the truth value we see under P, and not Q is going to be false, true, false, true, going down the rows, because Q was true, false, true, false. Okay, then the inverse is going to be the implication between these two negations. So not P implies not Q. Now, the rule for assigning truth values to an implication is true most of the time. It's true in all circumstances except when the first statement, the condition if you like, is true, and the second statement, the conclusion, is false. So that only happens in the third row of the table there. So in the third row, the implication here for the inverse is false, but in all other situations it's true. Okay, then we deal with the implication Q implies P. So we're looking at the second column of the truth table implies the first column. Again, it's an implication which is true in most situations and only false where the condition, which is this time Q, is true, but the conclusion, this time P, is false. So again, you see that's only in the third row of the table, where you have Q true and P false. In that situation, the implication Q implies P is itself false. But in all other situations, the implication is true. So we have true, true, false, true here. So then we just need to just make the observation that in these final two columns we always have exactly the same truth value. So that shows that these two statements are logically equivalent.